Okay, I think we'll go ahead and start. It is promptly 8:30. People will maybe join us as we come along if we have some more coming in. But it's a little redundant, as I said. My name is Gary Moore. We're happy to be doing this today with UE Systems. We are hosting this on behalf of UE Systems, or Alpine Components, our partners in the UK. We got Chuck Peterson, who has a tremendous amount of experience on this electric motor bearings and how we diagnose them. So we're really thrilled to have Chuck with us and taking up his time getting us to do this for us today. Let's all welcome Chuck Peterson, taking up down in Kansas, right? You're out of Hutchinson, Kansas, Chuck?
That's correct.
Yeah, on board with us here today. And with this, Chuck, what I'm going to do is, if you're ready for me, I'm going to change this over to you.
We're ready.
Okay, and I'm going to turn it over to Chuck, and we will let him do his thing. There you go, Chuck. I'll let you take it from here.
Okay, thank you. Good morning, everyone. A little bit about Peterson Predictive Maintenance. We started about 7 years ago. Actually, we started the business only doing infrared. We were doing a lot of infrared on motors and stuff, and we caught wind of the ultrasound, and in meeting with Alan and Gary at UE Systems, we ventured into the ultrasound aspect of predictive maintenance. And once we brought the ultrasound online, immediately our business doubled. It was amazing. The ultrasound, people understand more. You can talk to the people that are in charge of the predictive maintenance programs, and they're more receptive to the ultrasound than they are infrared. Infrared is kind of witchcraft to a lot of people. Enough about Peterson Predictive Maintenance, a little bit about me. I've been in the business, as I said, for 7 years. I retired from the fire department as an arson investigator and then went into predictive maintenance, used to work for a large gas company here in Kansas, and started their predictive maintenance program there. In 2 years, we took their mean time between failure from 2 pumps a month to 2 pumps a year. And we were in charge of 93 pumps and motors to keep all of them running. That plant, if it shuts down, it's $150,000 a day loss. So in production, so they, obviously don't want to shut down. So some of these programs that we're going to talk about today, they have been installed in several plants, and they do work. So some simple things that a lot of people don't think about it a lot of times. So we'll start the presentation here. As we go, we're going to play some sound, and we're going to listen to some examples. To start off, obviously, I'm Chuck Peterson, president and owner of Peterson Predictive Maintenance. My email address is not on here. I'm going to give it to you now. So if you want to write it down, it's chuck@petersonpredict.com. It's pretty simple. And so if there's any questions come up, obviously contact Gary or one of the fine staff at UE Systems, or you can email me direct, and we'll see if we can help out in any way we can. Again, we want to thank UE Systems. They are the backbone of our company. Without UE Systems, we certainly wouldn't be here today. So enough with the propaganda. Let's move on. So what we want to do today is I want to challenge everyone listening to think outside of the box. That's what it amounts to. We have to think about things that we've never been able to hear, things that we've never been able to see. Since we were little children, if we heard something we didn't like or we were afraid of, we covered our ears. It's the same thing with sight. If we've seen or heard something, if we've seen something we didn't like or we were afraid of, we'd cover our eyes. Well, we have to get away from that mode of thinking. We have to start thinking that those sounds and those sights are here to help us. Ultrasound extends our senses so far that we can actually hear things that we cannot hear with our ears. An example is a dog whistle. How do you know a dog whistle works? Well, I guess if the dog comes or his ears perk up, you know it works. But other than that, somebody could sell you a piece of tubing and tell you it's a dog whistle. There's no way you could hear it. The frequency is too high. Thinking outside of that box. That's what we have to do. We have to think of what is there that we can't see or we can't hear. Ultrasound and infrared will allow us to do that. It's also non-intrusive testing. It's the safest way to test. We just touch it or we look at it with the instrument and run our test. Obviously, the machine does not need to be shut down. We require a minimum of 40% load on the machine so we can get accurate tests. changes in the operations. So we're not going to upset the plant or change operations or get an operator mad at us because he's got to shut one pump down, start another one. There's no problems with change in operation. And it costs less to test this way because it is non-intrusive. So those are some things we need to think about. I've used ultrasound in every one of these applications. Now, I'm not going to sit here and bore everybody talking about every application, but you can see by thinking outside of the box and thinking what could be there, you start to hear things and you start to see things that you haven't been able to do before. Compressed air leaks, the biggest bang for your buck with ultrasound. I can go into a plant and pay for the survey, pay for the whole predictive maintenance program. In a lot of cases can be paid for just by fixing their air leaks, the money they will save. Biggest bang for your buck. I would really recommend somebody really look at that one hard. Bearing monitoring, condition monitoring, bearing rubs, pump cavitation, gearboxes, pumps and motors, lubrication. It just goes on and on and on. And once you start to think and start to imagine things outside of that box, a lot more of these things open up to your mind to see what's going on. Whoops, went one too far. So there are some things that in our programs that we install in facilities that we recommend that they do prior to hitting the start button. Okay? The first thing we want to do is we want them to pull the grease tubes out of the motors and verify that the motors have been greased. In today's world with EPA and environmental protection, most motors are shipped dry. Now, the motor company doesn't tell you that. And there's a reason they ship dry. Is because some people are using a moly-based grease, some people are using a poly-based grease. Those two, moly and poly, don't get along. The two of them mixed together form an acid that will eat the race out of your bearings in 3 to 5 years. So we don't want to mix the two. So to get rid of the problem of mixing the two, motor companies don't grease the bearings. So consequently, in the last 6 months, I've found 50 motors that we pull the grease tubes out of them. They're dry. They're empty. People get a new motor or a rebuilt motor. They take it off the crate, install it, align it, hit the start button, assuming brand new motor, it's ready to go. Well, it's not. It's not. We have to make those motors ready for service. Very, very important. The next thing is a shaft run-out test. We take a dial indicator, a magnetic stand, set it up on the shaft, and roll that shaft over from the keyway all the way around to the other side of the keyway. If that dial indicator moves more than 0.03 of an inch, we will not accept the motor. The shaft is bent, or it's not in there straight, or something is wrong because it moves more than 0.03 of an inch. Remember, when we align a machine, it has to be within 0.03 of an inch, or we won't walk away. Well, if it's 0.03 of an inch to start with, there's no way you're going to get it in alignment. So we won't accept it. We're not an experimental field. Remember that plant, $150,000 a day? I can't put that motor in and take a chance of that plant being shut down. So 0.03 of an inch, that's the maximum that we'll accept. Bench vibration tests are very, very important. We're going to see some things today on spectralizer that will show you that the spectralizer runs on the time domain and the FFT scale, which is exactly the same thing that vibration tests run on. So I want to know where those bearings ring out with that machine unloaded. I need it documented. So when I load it up, I have a comparison. The next thing is an amp draw test. This one doesn't seem important, but it's very important once we think about it a little bit. When we first put that machine in, when we first line it up, got it coupled, we want to run an amp test before we couple it up. So start it up. When you check rotation, take an amp draw test, all 3 phases. Document that. Then let's load it up. Let's go ahead, couple it up, get it ready, and we'll take another amp draw test. Document that. Well, now 6 months or a year down the road, if we start having trouble with this pump or this machine starts to give us some problems, we take another amp draw test. When we loaded it up new, if it was drawing 10 amps per phase, and now, since we're having problems, it's drawing 18, or maybe it's drawing 10 on A and B and 22 on C, that's a problem. That's a way that we find or we look for to indicate the problem developing. So AMP tests are very, very important. This is a long ways from ultrasound or infrared, but these are indicators that will tell us that we're having a problem. Okay? So we move on. Some of the problems that can be detected with infrared or ultrasound, soft foot. For those of you that don't understand what soft foot is, there are some people out there that have never heard of it. The plate or the base that the motor sits down on is supposed to be milled even. The feet on the motor are milled even. Well, sometimes you have a three-legged stool. You set a motor down, and even though it's sitting down and it feels solid, there's actually a little bit of a raise on one foot or the other. So what we do is we'll take dial indicators and find that soft foot. The next slide will show us that. Then there's misalignment. Misalignment is very, very important. We talked a while ago about 3/1000ths of an inch. Most business cards, if you put a mic on a business card, most business cards are measured. You can measure those, and those are 6/1000ths of an inch thick. So just think about that. Center line to center line on alignment has to be half the thickness of a business card, less than half, in fact, because we want it inside of 3/1000ths. Okay, we're going to look at some greasing problems today. One of my biggest pet peeves is greasing, and you will see that today. We're also going to look at some mechanical looseness, maybe some cavitation in a pump, and some competitive noises that we will find. So let's move on. This is the soft foot. This was found with ultrasound and infrared. Ultrasound, we looked at it first. What we heard actually was, and I'm going to play it. Let me move this over here so we can play it, and I'm going to put this on dual so we can open the file. Come on, file, open. Okay, we're going to play the soft foot before it was corrected. I want you to watch both screens and listen for the surge. You'll hear the surge in the motor running. Okay, here we go. Okay, that's the surge in the motor. You could hear it. You could also see it in the time domain. You see them getting bigger and smaller and bigger and smaller. What happened, and I think most of you can see my mouse moving, this foot right here, the front foot on the right side, we put a dial indicator on the base and put a dial indicator on that foot, loosened that bolt. Excuse me, that foot raised 0.010 of an inch when we loosened that bolt. So we tightened it back down, went all the way around. The opposite corner, caddy corner across, also raised 0.010 of an inch. So basically what we done when we bolted that motor down, we put a twist in the case. Now the twist in the case is noted right here. You see the heat in the motor? The tolerances inside of that motor between the rotor and the stator are so small that a little bit of a twist in that case shows up pretty quick. You also hear it with the surge in there. Okay, this motor is too hot, and the hot spots are showing up in it. So let's go back to our spectralizer, and let's stop this one. And I'm going to play after we corrected that. Now, for the correction, what most people would think is that you put 0.010 under that one foot. Well, that's not true. We put 0.005 under the front one and go caddy corner and put 0.005 under it, because remember, the motor's tipping. So that way we took it down square. Now listen to the sound of it now. You notice the surge is gone. Your time waveform is all even all the way across. It doesn't have the fish in it like it did before. And the spikes are gone in the spectralizer. So it's very important. So this soft foot that's a $23,000 motor, 2,300 volts, 300 horsepower, and it runs a 15-stage pump going into a pipeline. Very expensive machine that was fixed with two 5,000 shims. It's pretty prominent, pretty big deal. So misalignment. It's been our experience that misalignment is the second leading cause of premature motor failure. Misalignment. What is alignment? A lot of people say, well, it looks square. I measured from hub to hub, and it's a 1/2 inch on both sides. Well, that's not good. That's not an alignment. We're talking alignment to within 3/1000ths of an inch, okay? So what is alignment? We'll talk about that. How would it sound with ultrasound, okay? How would we know that it's misaligned with ultrasound? How can we confirm the misalignment? What damage can be done through misalignment? Is it a hard test? Is it complicated? No. And can it add to the bottom line? Well, when we're talking about shutting down a $23,000 motor and a $150,000 a day pump, certainly can add to the bottom line. Certainly can add to the bottom line very quickly. So let's look at misalignment. Misalignment is when two separate machines are coupled together through a coupler, and the two shafts are not aligned to within 3/1000ths of an inch center line to center line. This places undue stress on the inboard bearings on both machines and severely shortens the life of those machines. Now, for the sake of terminology, we're going to look at this machine, and the two bearings we see, this one here is the inboard bearing on the pump. This is the inboard bearing on the motor. The outboard bearing is where the fan is. The outboard bearing on the pump is where the impeller is. So the two inner bearings are the inboard bearings for sake of terminology. So usually we have two inboard points. How are we going to know with ultrasound? If we take an ultrasound reading on the outboard bearing of the motor, and then one on the inboard bearing of the motor, then one on the inboard bearing of the pump, and outboard of the pump, the two inboard bearings will be noisier or louder than the two outboard. The reason for that is the stress that we're putting on it through that coupler, because those two shafts are not aligned properly. Okay? So there's a way we can do that. How are we going to confirm it? You know, somebody's not going to say, yeah, you're listening to it. There's no way you can tell. Well, we have other options. We have infrared. We have vibration. Just simply realign the machine. There's several different ways that we can confirm what we're looking at. What we're going to do is use infrared. We see here, this is the same machine. Notice the stress that's placed on the inboard bearings of both machines. Look at the heat here. The lighter the color, the hotter it is. So the stress on the inboard of both of these machines is tremendous. It's like trying to turn the hinge over. You know, you've got it in a bind, and all the stress goes out that shaft straight into those two bearings, because that's the first give point. So it very, very severely shortens the life of this machine. Let's look at this one. This motor, to the naked eye, appears to be fine. Nothing wrong here. It looks good to me. Put ultrasound on it. The outboard bearing was quiet. The inboard bearing was very noisy. And going on across to the pump, the inboard bearing on the pump was noisy. So let's look at it. Here we go. In testing with ultrasound, confirming with infrared, there's severe misalignment. Look at the stress put on the inboard bearings here. Look at the heat that we see on both of these bearings because this coupler is out of alignment. There's several ways to align machines. Personally, I like reverse angle. Most people like lasers. Laser alignment is fast, it's quick, it's accurate, it's very good. But I'm kind of the old turn it with my hands, screwdriver and wrench kind of guy, and I like to, if I have enough time, I can generally pull them down to dead zero. Let's look at this machine. This machine looks like there's nothing wrong with it at all, except the bearing is hot. We can tell this bearing is hot because of the grease. Look at the grease running out of here. That's a telltale sign already, and we'll talk about that in a little bit. But this machine looks like it's okay. Well, let's look at it under infrared. We see the stress on the inboard bearing here, the stress on the shaft getting hot here. Look at this. This is a Martin-style coupler. It's the one that has the little rubber gear in the middle. Well, everybody's taken wire and bent it back and forth till it breaks. It gets hot. That's movement of the molecules. It's weakening it. That's exactly what's happening here. You have two hubs that are working that rubber, squeezing it, compressing it, letting off, compressing it, letting off. It just heats the rubber up. This is severe misalignment. When it starts making the rubber in the coupler hot, it's a bad deal. Okay, so here we go, misalignment. Now we've proven misalignment with ultrasound because the two inboard bearings are louder than the two outboard bearings. We've also confirmed it with infrared. Vibration is going to show us the same thing. If we go out to vibration, we show spikes on an accelerometer, we show spikes at 1 to 1.5 times running speed. Again, another indicator of misalignment. So very, very important. And it all starts with that shaft run-out test when that motor comes into the plant. Very, very important. Look at this machine. Look at this machine. There's not a problem. Obviously, it's got a few leaks. We can see where some process has been leaking out of it. And they just keep replacing, just keep replacing. Well, you know, if we look at it now, we can see what happens. Look at the stress put into that pump from misalignment. This machine failed 3 days after these tests were run. The manager had the reports but chose not to use the information. Led to a plant shutdown, and of course, that was not planned. Very, very important. Misalignment is the second leading cause. I stress that, the second leading cause of motor failure. I have actually aligned motors that you couldn't turn the coupler over with a pipe wrench. When we got done alignment, you could lay your hand on top of it and let it fall off, and the motor would coast down to a stop because you've taken the stress out of those inboard bearings. It's very, very important. Okay, so let's move on. Misalignment. Testing for misalignment is very simple. You must test the outboard and the inboard bearings for each machine. If the two outboard bearings are significantly quieter than the two inboard bearings, then we have a very good indicator of misalignment. If you suspect misalignment, try to confirm it with another technology such as infrared or vibration, or just simply realign the machine. It doesn't hurt. Doesn't hurt. Machines will settle and move over time. So just because it was the line to start with doesn't mean it stayed there. They will actually rise with heat. So they may be moving into misalignment. That's something we also need to look at. Misalignment itself is the second leading cause of premature motor failure. And it costs thousands and thousands of dollars every year. It's one of my second pet peeve, I would think. So, okay. If misalignment is number 2, what is number 1? And we'll go from here, and I have this for anybody. Usually this is the live deal, but if somebody out there wants to raise their hand and guess it, we'll give them credit for it. But we'll just move on. Improper lubrication. Improper lubrication is the leading and bar none number 1 cause of premature failure. How much grease is enough? How do we know? How many of you know how much grease comes out of your grease gun in one stroke? Not very many, because nobody pays attention to it. Okay, what we recommend is you take, if you have nothing else, take a 1-ounce shot glass and count how many strokes it takes to fill that shot glass. If it takes 10 strokes to fill that shot glass, then 1 stroke is 1/10 of an ounce. It's pretty simple. So now what we've done is found a way of measuring how much grease we're putting in there. How often do we grease? The book says we should grease every 3 months, okay, whether we need it or not. Well, I disagree with that. If I've got a motor that's sitting here running 24/7, and it's running under loaded conditions, and I've got a motor sitting right beside it that runs 2 hours a day under loaded conditions, the book says grease both of them every 3 months, whether it needs it or not. Well, obviously, that's wrong. You're going to over-grease a motor that runs 2 hours a day and probably under-grease the other one that runs 24/7. So we have to start using another medium to grease. So we recommend we use ultrasound. Ultrasound is the best way to grease. Excuse me. What type of grease do we use? The first thing we do when we go into a plant is we look for their grease guns. We open them up and see what they got in them. If they've got multi-purpose grease in their grease guns, we pick it out and throw it away. Multi-purpose grease is not for electric motors. Electric motor grease is for electric motors. Okay? Need a good SHC 100 in the United States. I don't know what the equivalent would be in the UK, but you need a high-temperature, high-speed grease made specifically for motors. We give them a paint gun, We give them a grease gun and paint it hot pink or Day-Glow orange or something. We put that motor grease in that gun. Now that gun is used for nothing but electric motors. That's it. No other grease gun is used for electric motors, and that grease gun is used for nothing but electric motors. That way we got the right grease going into the motors, okay? So What does ultrasound do for greasing? What equipment does it take? Ultrasound for greasing is the best thing that ever happened to electric motors, and we're going to prove that today. The equipment that it takes, I use the UltraProbe 10,000. There are other mediums to use. UE Systems has the Grease Caddy. They have the other ones. I don't even consider anything but the UltraProbe 10,000. As far as I'm concerned, there's not another machine in the country. I won't use anything but that. But let's look at this. How many of us have seen this around motors? Okay? What's happened here is this motor's overgreased. Now, what happens when we overgrease a motor is as the bearing turns and the balls rotate around the race, it forces the grease to the outside. That makes a tunnel if we've overgreased, and now the grease becomes an insulator because it can't get the heat away. Once the grease becomes hot enough to break down the base, the moly or poly that's holding the oil or lubricant in the grease, then it slings it to the outside. Once it slings it to the outside, we start to see leaks around the end bells right here. We start to see it drip from the shaft seal, and we start to see a motor heat up. Well, that's what happens when we overgrease a motor. Contrary to what a lot of people believe, for an example, electricity does not run through the wire. It runs around the wire. That's why when we put an amp probe around the wire, that's what we're testing, is that magnetic field. Insulation on wire is not to keep you from getting shocked. It's to direct the flow of that current. So if we overgrease this motor, and that grease gets back into the varnish and the windings on the motor, the grease breaks down that varnish or insulation. Now the current's not going the right directions. It's jumping all over everywhere. So our motor loses power, RPMs go down, the motor starts to heat up, it starts dripping grease. What's the first thing we do? We put more grease in it. And that's what killed it to start with. This motor right here, I asked the guy, how much grease do you put in it? He told me. I'll get to that here in just a second, okay? He said it's a 25 horsepower motor, so that might give you a hint. We've all seen this. Look, here we are again. We're greasing, we're running grease around, leaking out around the end bells. It's dripping from the trough. Look at the heat. It's starting to heat the motor up. A lot of times we'll find this from misalignment even, because what it is, it gets noisy from the stress, so they pump more grease in it to quiet it down. 10 minutes later, it's noisy again because the bearings are running crooked. So we end up overgreasing the motor. I asked the guy, how much grease do you put in the motor? He said, well, it's a 25 horsepower. I said, yeah, I know, but how much grease do you put in it? He said, well, it's a 25 horsepower. I said, what's that got to do with it? 25 horsepower, you put 25 strokes in. I thought, what kind of logic is this? Do you put 600 strokes in a 600 horsepower motor? Come on, we got to wake up. Now, you know, I thought he was giving me a line, but he wasn't. There's that 25 horsepower motor. Look at the inside of that motor. No wonder it was heating up. No wonder it was losing power. Look at the grease inside of there. It's amazing. And we find this every day. Every day. This one is not bad. Look at this one. This is a 60 horsepower motor that's running a paint vat in Wichita, Kansas. It was running a paint vat. I got a couple things to say about this one. Number one, this guy would no longer be working for me. After about the 7th or 8th tube of grease, somebody needs to ask the question, where's it going? Obviously, we can see where it was going. The second thing is, and this is a real problem, notice this bearing. Notice this? That's a shielded bearing. Grease can't get in that bearing if we wanted to. So what happened here? Why does it have grease zerks in it? I asked him. He said, well, the new motors we got didn't have grease zerks in, so we pulled the plugs out and put grease zerks in them. They did that not knowing that that plug is a signal it's a shielded bearing. So they put grease in this motor and never touched the bearing. So they lost the motor. This is something we've got to really be careful about. If it doesn't have grease zerks in it, it probably has shielded bearings. Brings up another point. I will not accept a motor with shielded bearings in it. I want to grease my bearings. Even if the bearing is started to go bad. If this bearing started to go bad, you can grease all day long, and you can't baby it through till shutdown because you're at the mercy of the shielded bearing. I want my bearings open where I can grease them. Even if it goes bad and I have to stand a man there and put a shot of grease in it every 5 minutes until I can get to a scheduled shutdown time, then that's what we'll do. But at least it gives me that ability to baby that machine along until I can get to a scheduled shutdown. Very important. I will not accept shielded bearings because I grease with ultrasound, because I grease the right way. Let's grease a motor. This is a 100 horsepower motor running a 1,500 gallon a minute pump, and we're going to grease it. So we're going to look at this wave file. This is the baseline. Listen for the crackling and the popping in the bearing. What that is the grease separating. Okay, here we go. Now you can see on the time waveform and the spectralizer. Spectralizer, it's really a pretty clean image. There's not a lot of high peaks or spikes in there. The noise is in the time wave domain because you can hear the bearing, the grease separate and popping. Okay? Well, let's grease that machine. So now this is why we grease with ultrasound. There's no question about what's going to happen here. Okay, listen to it this time. I don't have to say any more. That sells it all right there. You can hear the grease hit the bearing. The thing ultrasound's going to do is it tells us when the bearing needs grease. It tells us when it's got enough grease. We will never over-grease another bearing. It's that simple. It's just that simple. You could see the noise come down. You could actually see it lowering itself. The white bar across the time wave domain, all the spikes are gone. The bearing has been properly greased. It's just that simple. Do not we have several plants that have totally quit greasing their bearings. They don't grease anything. We go in once a month. We run all of their machines. If the bearing needs greased, we grease it while we're there. So their grease program has been taken completely over by our company, and their motor failure has been cut by 70% because they're no longer over-greasing bearings. Well, let's move to another one. Let's see if we can find another bearing here we can look at. This is a 600 horsepower motor. So let's listen to bearing number 2 and see what it sounds like. So we'll go to the wave file here. And I might also say, while I'm on here, these wave files and this whole program are available online. So this is the bearing when it's dry. Again, you can see the spectralizer is a fairly clean image. It's not got a lot of big spikes or high spikes. And look at your time waveform again. A lot of clutter, a lot of dirty stuff in there. Okay, let's grease this one. And I have to warn you, this one, the grease hits it pretty quick, and it's right near the end. So listen pretty close to this one, and we'll see if it quiets down for us also. You notice in that one, it took a little longer for it to quiet down. It's a bigger motor, took a little more grease. And the other thing in that one, at the end of it, you could hear the clutter kind of go away and then come back and then go away and come back. This is the first time we run that machine. What had happened, but it had not been greased. So remember we talked earlier about the balls pushing the grease to the outside? That's exactly what took place here. As we put new grease in it, the old grease was dry and crusted, and we had to force it on through the bearing to get it to quiet down. And that's exactly what happened here. And you still see in the time waveform, there's a little clutter there now and again, but that's the old grease working its way through the bearing. This motor finally quieted down to where it was sounded like air escaping, the way they're supposed to. Again, a perfect reason why ultrasound should be used to grease bearings. There's no other way to grease a bearing. There is no other way, just that simple. And that happens on big machines. Let's look at this machine. It's not very big. It doesn't look all that big. That's a vertical motor. It's 200 horsepower. Okay? Underneath there, this little gearbox right here is a 7-to-1 increaser. There's a pump right down here on the bottom that has a 4-inch impeller in it. That impeller is turning 25,700 RPMs. So now, if we have a bearing lockup in this machine, I've seen those motors fall off the top of the pump. It just breaks them. Everything just breaks to pieces. When we start this machine up, we hide behind the I-beams because it just screams. So you can see the importance of properly lubricated bearings. So in the interest of time, I'm not going to go through and run all these bearings, but I wanted you to understand and see perfect examples of what using ultrasound to grease bearings will do for you. Well, then people say, how should a motor sound? You showed me some bad ones. Let me hear a good one. Okay? Well, we have one. So let's bring the spectralizer back in. Also, you might notice we're using spectralizer 4, which is now available online. Everybody should get a hold of that and use it. You can see the advantages. Listen to this one. This is a good bearing. Okay, you can see I had the volume turned way up on my recorder, but it's clean. It's symmetric across at 100. Look at the line on the time on the spectralizer. Let's switch it back to the spectralizer, and I'll run it again so we can see how clear it is. So you can see the line there. That's a pretty clean line. Notice how it sounds like air escaping. You know, you take an air hose and just push the button, and that's the way it should sound because it should be smooth, no noise in it. So those are the kind of things that we use ultrasound for greasing. Again, there's no other way to grease bearings as far as I'm concerned. The other thing about this motor, spectralizer is going to show up here because I shut it off instead of moving over. The motor's good. This of the motor. That should always be the warmest part of a motor. If you have a hot temperature out here or one back here, then you got a bearing problem. Anytime you have it warmer out here on the inboard end or the outboard end, if it's warmer than the center of the motor, you have a bearing problem. It's that simple. We don't know what it is yet. Could be misalignment. This happens to be a belt-driven machine. We may have the belts too tight. Could have soft foot on this motor. There's several different things, and which brings up a point. Soft foot is very seldom ever checked on belt-driven machines. How do we know that that base plate is square and level? We don't. We should always check those machines for soft foot, but we don't. People just don't do that because it's belt-driven. It's very important, soft foot. Okay, but when we start this motor, when it actually gets up to running speed, it finds a magnetic center up and down. That's where it runs. It also moves axially as much as it can to the magnetic center to run that machine. I mean, actually all a motor is one magnet chasing another one. So once it gets to that magnetic center, your bearings are unloaded. There's no reason they should be hotter than the center of the motor. Unless we have a misalignment, a dry bearing, a soft foot, we're putting stress on the bearings of some nature. So this is a very good signature pattern. So now with ultrasound, we listen to the air escape. With infrared, we see a very good signature pattern. This motor's fine. This motor will run for a long time as long as it stays in the condition that it's in. So a little bit about the spectralizer. We're going to talk a little bit about real quickly about bearing fault frequencies, and what we have here is a formula. This formula is available through UE Systems. Gary can get it to you. We've tried to simplify it a little bit, but vibration you can tell by taking 3 readings and they cross with each other and get your ring out. You can tell if it's inner race, outer race, ball pass, or cage failure. We can do the same thing with ultrasound. I used to do vibration for One Oak Gas Company here in Kansas. I did it for about 6 years. Used CSI equipment, RBMware, and 2120 vibration analyzer data collector. I quit using vibration because I can do it quicker, get better results with ultrasound. With vibration, you have to take 3 readings, X, Y, and A reading. With ultrasound, I take 1 reading and move on. Okay? So we're going to apply this. So let's take this formula. If we take 4.4 times the number of balls in the bearing times the turning speed and divide that by 60, that would be the fault frequency for the outer race. Okay? Let's apply that. So if I bring in this little spreadsheet here that we've made, and if we take 0.4 times the number of balls, let's say this is a 318 bearing we're going to use, and I know it's got 8 balls in it, okay? And the tag speed on the motor. On the tag, it gives you the RPMs. Well, this one happens to be 1750. So if I enter that, then my fault frequencies are automatically calculated for me. 93.33333 is going to be my outer race fault frequency, okay? Let's remember that number. I'm going to move this out to the side for a second. We're going to move this over, and we're going to look at a motor. This is an actual case scenario that I had in a town about 60 miles from where I live. It happens to be an ethanol plant. The ethanol plant, this is the number 5 circulator pump. It's a 100 horsepower motor. If we look at the inboard bearing on the infrared, if we look at this small little cross right here, that cross is that temperature. So we already know the inboard bearing on this thing is pretty hot. 195 is pretty hot. And also notice that it is hotter than the center, that center band on the motor. We got a bearing problem. That's simple. So we start checking. New bearings cost us about $3,000. Time we get them in and everything back up and running, we're about $3,000 in cost. A new motor, I talked to the manager of the plant. He said about $6,000. A new motor was a week to 10 days delivery. Okay, so repairs on a planned shutdown, we could get it done. You know, high side, we're looking at $6,000 to $8,000. Okay, well, that's a bad bearing. We know it's a bad bearing. Let's play it. Let's listen to it. Okay, so we're going to go to File. We're going to open it up here, and we're going to play that bad bearing. Now, I want you to listen to the tonal quality. Remember, we're listening for air escaping, right? Listen to the bassy sound in this machine. Okay, here we go. You hear the bass in there? What happens is when we get, this motor's turning so fast. Remember, our tag speed was 1,750 RPMs. There's 8 balls in that bearing. So 8 times 1,750 for each revolution, that ball is hitting that pit in the race. So they're so close together that we can't hear. It sounds like a bass sound. We can't hear between the clicks. So it sounds bass. The tonal quality of that motor is gone. Now, if we also, and let me do a little bit of change in here. I'm going to bring this down where we can see it. So now, if we look at the spikes, it's not clean like the air sounded a while ago. It's not clean. So we need to find out where are these spikes. Well, I'm going to spread this out a little bit so we can see it a little easier. I'm going to make that a 1, and now this is the shining moment for the spectralizer 4. This is just awesome. So if I go right here and hold the shift key down and left click, you see it puts a harmonic cursor in there. Well, that harmonic cursor right now is on 87, but you notice as we move out across the spectralizer, we get farther away from our spikes. Well, if we go down here, we can jump that up by 1. We can jump it up again, and let's go to 90. Let's go to 91. Now look at 91. Let's take these tenths off, and let's just see how close we are. Look at 91. We are banging every one of those. Well, remember a while ago it said 93.33333, but also remember that our tag speed on that motor was 1750. Well, maybe that bearing's bad. Maybe that slowed the speed down a little bit. The bearing being hot, it's got drag on it, may have brought our RPMs down. The load on the machine, the pump, may have brought our RPMs down. So this is the only variable we have. So let's change this to 1735 and see where we go. Well, now we're at 92. Well, let's drop it down a little more. Let's go to 1710. Whoa, 91. Is that amazing? Look at this, 91. Outboard bearing, the race on the outer race on that bearing is in failure. It's that simple. Cut and dried. No way around it. It's got to be the outer race on that bearing is in failure. Look at our spikes. Look at our outer race failure number. I'm going to bring this over and put both of these on the screen, I think, where we can see them. Yeah, here we go. 91. Look at our outer race failure. Dead on 91. It's cut and dried. It doesn't take a rocket scientist to see what we got going on right here. So I tell the manager of the plant, we got to shut this down. We got to fix it. He said, no, you don't understand. Plant makes $35,000 a day. We cannot shut this machine down. Well, this is where predictive maintenance gets tough, because, you know, I can show you all the data. I've just shown everybody here all the data. I can lead you to the water, but I can't make you drink it. You know, I can show you what's wrong. I can prove to you what's wrong. I can do it with ultrasound. I can do it with infrared. I can have you listen to it. I can have you look at it. But I can't make you shut it down. Somebody's got to make a decision. In this case, if somebody doesn't make a decision, the motor will. The motor will make the decision itself. You know, it's going to be at 2 o'clock in the morning when there's no staff here and there's 4 foot of snow and the wind's blowing 60 miles an hour. It never happens at a convenient time. It always happens when we're pushing it the hardest and using it the most. How many people ever lost a motor? Now be honest. How many people ever lost a motor when they did not need it? It don't happen. It don't happen. It always happens when we need it the most and we're pushing it the hardest. So he says we're not shutting it down. So let's let it run to failure. Okay? So it runs to failure. The plant makes $35,000 a day. Let it run to failure. You got 10 days waiting on a new motor. 10 times 35 is $350,000 in lost production. And ladies and gentlemen, I'm telling you right now, you cannot get lost production back. You're already running at 100%. You can't run at 130. You're running as hard as you can go right now. So lost production is just lost production. Product out the back door. You don't get it back. You lost it. Okay? That's a $350,000 loss straight away. Plus the cost of the new equipment, all the repairs. What about collateral damage? When this bearing locked up, did it twist the pump off the impeller shaft? You know, we don't know. I mean, it could have. It could. So potentially, by the time you add collateral damage, manpower, overtime, this job could cost upwards of $500,000. That's a lot of money for something that we could have fixed originally with the shutdown for about $6,000 to $8,000. Well, you go tell your boss that. I don't want to tell my boss that, because if I tell him we could have fixed it for $6,000 or $8,000, but it's going to cost us $500,000, I probably am not going to have a job. Okay? This is what predictive maintenance, ultrasound, and infrared will do for you. This is the silver bullet. Now, people I've heard talk before say there's no such thing as silver bullet. I contend that they are wrong. This is a silver bullet. Okay? And I'm going to show you how to use that. We've got a few minutes left. But before I do that, I want to show you one other thing here. We talked about competitive noises. Okay? So this is a brand new installation in Fort Collins, Colorado. It's the water treatment and city water services. And they didn't know they had a problem. We went in and set baselines on all these machines. These are vertical pumps, and you can tell they're pretty high, and they're very high dollar pumps. So what we're going to do is this pump right here is the one giving us the problem. So I'm going to stop this, and I'm going to play it when we first listen to it. Listen to this ugly one. Let me get rid of that. Okay, here we go. Now that's scary. That was down on the pump. That wasn't the motor. It was down on the pump. And I can tell you, when I heard that, we started backing up. It was scary. That's ugly. But now, what we listened to there is cavitation. It sounds like mechanical looseness, but it's cavitation. What I done was I moved to the discharge on the pump, and I actually closed the discharge of the pump down 1/2 of a turn. 1/2 of a turn on the discharge, and it made this difference. You can see the difference there. We saved that pump. There's no question about it. No question. That pump would have just beat itself to pieces. So now the plant operator says, well, yeah, but you've shut you've shut me down a little bit. You know, my efficiency's down because you closed that valve down a half a turn. Well, it comes down to cavitation is gas or bubbles, or it's trying to pull it through there faster than it can get it. So he can run wide open and 80% efficiency, or he can shut it down a half a turn and run 100% efficiency. A lot of dollars been saved here. That's the difference. Those are the things that ultrasound will do for us. They didn't know that was even taking place because they couldn't hear it. With the ultrasound, we picked it up immediately. Okay, so let's move on. We talked about silver bullets. There's a couple of things in the last couple of minutes here I want to talk about the silver bullet file. It's been past history that anytime we cut the bottom line in a facility, especially manufacturing, the first place we do is we cut maintenance, because maintenance doesn't contribute to the bottom line. It's that simple. They protect it, but they don't contribute. They don't put product out the back door. They're not operations. So what happens is the guy comes in and says, look, we've got to cut the bottom line. Half of you guys have a job. The rest of you guys are laid off, okay? Oh, and I want to also tell you, the half of you that keep your job, you're going to do these other people's job, and you ain't going to get no more money. Well, so now we've got bad morale problems. We've lost half of our people. We've got to do twice the work. That's when the maintenance manager needs to stand up and pull out these silver bullets like the one we just showed for $500,000. Now, you want to document everything. You have to document everything, good ones and bad ones, silver bullets and corroded bullets, okay? We keep them all in the file. And we put the average ones in the middle, and or the good ones in front, and the average or bad ones in the back. Now I'm not going to show him the bad ones unless he asks for them. I'm going to show him the good ones. So when he lays off half of my crew, I'm going to pull these silver bullets out and say, look, here's the $500,000 we've potentially saved. Here's another $125,000. Here's another $125,000. You know, there's $800,000 we potentially saved this company this year. Tell me another department in this plant that does that. They can't do it. They can't do it. Okay? So now what we have is some leverage. I can go to that man and say, you can't afford to lay my people off. Look at the money we potentially saved here. In fact, you need to let me hire some more people so I can save you some more money. We have to turn the maintenance division into an asset instead of a liability. In order to do that, we have to sell ourselves. We have to talk in numbers, not wrench sizes. You can't go into that accountant's office with a hammer and a screwdriver and tell him you need $50,000. He's going to tell you that buy that hammer and screwdriver somewhere else, because he doesn't understand wrench sizes and horsepower. He understands numbers. This will allow us to give him numbers, and that's the thing. So with that in mind, I, again, challenge everyone to think outside of the box. Please continue to think outside of the box. Use your imagination. Ultrasound and infrared, the only thing that limits you is your own imagination. Because if you can hear the sound or you can make a temperature differential, you can find the problem. Okay? Now, a little bit of propaganda. These are things that we offer internationally. Of course, infrared and ultrasound detection, thickness testing. We also design, develop, and install programs with the above technologies. Again, real quickly, my email address is chuck@petersonpredict.com. And with that, I will turn it back to Gary for questions. And again, thank you very much for everyone attending, and I hope we learned some things today. Thank you.
Chuck, thank you very much. If you can hear me here, now I'm actually going to take this back from you.
Got it, Gary. Thank you.
That was just tremendous, Chuck. I can't thank you enough for all the time that you take to do these things. We really do appreciate it. I just want to say we actually gather a tremendous amount of information from our users out in the field, and so we really appreciate him taking his time. We have other learning opportunities with UE Systems and Alpine Components. Here's some energy-saving things that we're doing, these compressed air classes. If you have an interest in starting a compressed air class, or if you have some instruments already, get a hold of Jeremy and or John there at Alpine and get them up and running. Boy, it's a great way to save some money really quickly. We also do level 1 courses. We have about one a year in the UK. If you can't make them there, we have them going on constantly somewhere around the world. We've been doing some specialized steam trap testing classes. where we teach people specifically about steam traps. We're going to have another webinar in about a month specifically on that topic, on how to test steam traps using ultrasonic equipment. So if that's something of interest to you, look for that. We'll keep you notified as that comes. You can reach us here, UE Systems, anytime at info@uesystems.com. If you happen to be in the U.S. or Canada, there's our 800 number. For you guys out of the U.K. or internationally, the 914 number and our fax number. Any questions, you can get a hold of Alkine Components. There's their phone number, and there's John's email address. He's really good with the software and can help you with these things if you've got some questions, things you want to get going and done. This whole webinar will be recorded and put up on Alpine's website. If you have other people that might benefit from what Chuck had to say to us today, you can just simply pass that link on to them and they can watch it at their leisure. With that, I don't have too much more to do with it. I really appreciate everybody's time today, and we know you're busy. You got a lot of other things to do. Hopefully we brought you some value, and tune back in for future programs. Thank you.